Okay, welcome back. So today we deal with one lecture that is mostly focused on mathematics. And the purpose of this lecture is to sort of set the stage for the final formalization of all the topics and all the information we have gathered together in the last several lectures into what we will call the rules of quantum mechanics. That means a set of rules that basically define this theory and, and represent real fundamental information one must understand about quantum mechanics in order to proceed towards application. So say in the next couple of lectures, we will be able to distill a set of rules out of the ensemble of sometimes fuzzy informations we've gathered together. And these rules will define quantum mechanics in the most possible general broad sense. And anything that follows will represent basically a realization, implementations of these rules. So talking with some of you in the question and answer session live, so the course, I mentioned that up to this point, we've been somehow like crossing a river, and we were in the middle of the stream, in the middle of the river, where things are turbulent and complicated, and it's painful to walk through. I would say that the moment we define this quantum mechanics rule is the moment where all things we have said should kind of come in their place and sort of make sense all of a sudden together. And in this metaphor, that's when you step out of the river and you go back on ground, and you can turn back and see that you've done kind of quite a few meters in the water, but now things are on the other side of the river. So we're close to the moment where things should begin to make sense. But we still miss one piece of information for this to happen. And the missing piece of information concerns the mathematical structure of quantum mechanics, the language through which quantum mechanics is actually formulated. We've been discussing somewhat this in the couple of lectures before, but now it's time to sort of put things in order. So what we have been using and somehow discussing to this moment is the analogy between mathematical properties of wave functions and operators acting on wave functions, therefore mathematical properties of quantum mechanics in the end, and mathematical properties of vector spaces. So we basically show that after discretization, mathematics of so after discretization, basically the problem of solving for the Schrödinger wave function could have been mapped into the problem of finding eigenvalues and eigenvectors of a standard matrix with high dimensional vector space, for the number of dimension being fixed by the number of points through which you discretize the function. Just look back the last two lectures of this. And in those two lectures, we also mentioned the fact that we are interested in exploiting this analogy to understand why Fourier transformation was such a useful object relating equivalent representation of quantum mechanics, building an analogy with the base changing operation in linear algebra. So now we're gonna sort of make one step further in this analogy and really define the mathematical structure of quantum mechanics basically in terms of this analogy. So what I'm gonna do, I'm gonna split my board in two. On the left hand side, I'm going to define the mathematical objects that are in linear algebra. So I will define vector spaces. We consider a vector space. And on the other hand, on the right-hand side, I will define and discuss the properties of the environment, mathematical environment, if you want, we use to describe quantum mechanics. Because you see, there is at least one fundamental difference that, distinguishes quantum mechanics from normal, to be represented as a normal vector space, that you can represent it as some kind of vector space only after discretization. That's one main difference, which means that you map into different type of vector spaces depending on how many numbers you choose to use in the discretization. You use 10 numbers, you map quantum mechanics into a 10-dimensional vector space. You use 100 points to define your function, and you map it into a 100-dimensional vector space and so on. So clearly, wave functions are not just vectors, are functions. So from a mathematical point of view, the object that really is the natural environment for quantum mechanics is not that of linear algebra vector space, but space of functions, if you want, and this is called a Hilbert space. So we will define the Hilbert space as the natural mathematical environment, mathematical language, if you want, which is used in quantum mechanics. So the first important thing to be noticed is what I just said, that the number of dimensions is in a normal vector space is fixed unless they're infinite. And formally, a function is defined by infinitely many points. So if you really want to uniquely represent a function, you need infinitely many points. So in a Hilbert space, the number of dimension. So basically, some people say a Hilbert space is an infinite dimensional vector space. So the Hilbert space can be viewed as a specific realization of a vector space in which you operate, but such that the number of dimension of this vector space is not finite, as in the regular vector space you used to see in linear algebra, but is in fact infinite. So that's the first thing we want to know. But let me for a moment remind you one fundamental, what is a vector space? What defines a vector space? Well, we have mathematical objects, which are called vectors. And then so we call it V, W, Z, I'm using standard notations. And then, we can graphically represent in up to 3 dimensions, we can represent them as arrow. Of course, when we move beyond 3 dimensions, you cannot draw arrows in 4 dimensions. So we don't even bother drawing them. But of course, this is not the only thing that defines a vector space. We know that vector space is defined by operation between vectors. And the operations between vectors are, of course, linear combination. Now, in general, vector space can be complex vector spaces, which means that, linear combination can be complex number in general. In building this analogy with Hilbert space, let's build on the left the analogy with the vector spaces we are most commonly used to using, which are those in which the linear combinations are based on real numbers. So linear combination is a combination of multiplication of vectors times, say, real numbers for now. At least this is the vector space we are used in classical physics. And sum or difference, which is basically the same up to summing by coefficient -1 of different vector spaces, of different vector. And the main property of vector spaces, the defining property of vector spaces, is that any linear combination of vectors will lead a vector that still belongs to the same vector space. So if all these belong to a vector space V, then also the linear combination belongs to the same vector space. So let me just say, so I'll save some time, so space here. Okay. But there's a second, there are actually two more operations that are very relevant. One is inner product. Which basically is represented by saying V times W, and it's an operation that in this particular vector space is symmetric and projects vectors into real numbers. Again, you can define vector spaces that operate more generally, project into complex vector spaces with complex coefficients or complex vector spaces. But in classical mechanics, they're not, adopted. So we consider as vector spaces the vector spaces that are used in Newtonian dynamics, for sake of argument. And finally, there is the outer product, which is V, which I don't even bother writing here, or maybe I'll write by making some space. So the elements of the vector space are the vectors. Let's put it this way. And the operations between vectors and scalars are linear combination W equals AV plus BW, still belonging to the same vector space when this and this, A and B, are real. Then I have inner product, which is, V times W equals W times V, and it's a real number. And I want to emphasize that the inner product, before defining the outer product or external product, let me say that the inner product has an important properties of being bilinear. So in particular, the inner product between A, B, A, V, oh shoot, A, V plus B, W, inner product C, Z plus dt. So we are really, it's the vector space of linear combination. Then you can actually multiply term by term and get, a c v dot z plus a d d dot z, and so on, all the four terms. So this is called bilinearity. So the the inner product is bilinear. So let me just write it here like bilinear. It's linear in both terms that participate to the multiplication. And finally, we have the outer product. But we will not need that much. Now, in quantum mechanics, we will adopt, I want to, before we move into quantum mechanics, I want to emphasize one thing. When you define a vector space, you don't talk necessarily about coordinates. You can talk about vectors as general abstract entities which you draw by arrow without having to associate those vectors any set of coordinates. But if you want to teach a computer to manipulate vector, then you have to choose a basis, project these vectors onto that basis, and this operation of projection will generate the components of the vector in that basis. We'll get to that again in the next page. But you don't need to project to define a vector space. So you have basically two quantities. You have the abstract vector space, which you might be using for drawing arrows and making general consideration. But those vector space cannot be put down into numbers. These symbols here, these little vectors here, are found to draw. They represent elements of the vector space, but until I project them onto a basis, they are not associated with a set of numbers. I can represent that vector space onto a particular basis. And then for each vector, I will get a set of numbers. So there are basically two levels. There's the up in the air abstract formulation of vector spaces, which is the one we discussed in this half board. And then there's the ground to earth projected representation of the vector space after you choose a basis to represent. And this is done in terms of coordinates, components, and everything is so much simpler to deal with in mathematics. Okay, so I want to make sure you understand there's two like identical worlds. Sorry, not identical, but two different way of representing vector space. Two degrees of concreteness of a vector space, an abstract one and a concrete one. Okay. So let's remain for a moment at the abstract level, and then we see what happens when we move down to the more concrete level in both cases. Now, in quantum mechanics, the elements we will consider a slightly different object called the Hilbert space, where to begin with, the dimensions is infinite, as we just said. But also the elements have different names. The elements are denoted with a different symbol, which is this. This is called a cat symbol. For reasons that will become clear later. So why vector spaces elements are represented by arrows, the elements of the Hilbert space are called states, quantum states, and are represented by this symbol, which is called a ket. So this is a ket for psi, phi, maybe, I don't know. And my pen is dead, so I have to recharge it. Apologize for the small delay. And I'll use my finger. Maybe I call it psi. And so on. And of course, if I have operations, if I have elements, I want to define operations. And let's assume all the quantum states belong to a Hilbert space, which normally is denoted with H. Now, of course, I want to define operations between states. Apologize for using my finger to draw. So I think it's better if I stop recording pause my recording for a couple of minutes until the pen is recharged. Okay, so let's see. If my pen is now operating again, operations. Of course, I have linear combination. Which means that I can take a vector quantum state psi and write it as a linear combination of some state phi and of some state psi. However, unlike our analogy in classical mechanical vector spaces, the coefficients through which I define this linear combination are complex numbers. So the classical mechanic state, position, and momentum are vectors, and they are defined in a vector space where the coefficients are always real. The scalar product between two positions or a force and a position is always a real number. While in quantum mechanics, the linear coefficients are always, in general, complex. And the inner product is not exactly defined as in classical mechanics, because it's defined in terms of psi is represented by this symbol, but this is called bra and plays the same role of the first pair vector in a normal vector product. And this is the famous ket, through which the bracket notation, bracket, of course. So that's why they're called bra and ket. However, unlike the classical mechanical inner product, they are not symmetric. If you reverse the bra with the ket, you get a complex conjugate of the original inner product. And of course, for this to make sense, complex conjugation to be meaningful, this has to be a complex number. Now, the bra plays the role of a bracket, plays the role of a vector space multiplication. However, technically speaking, one should be careful that the bra is not really a vector. It's called a dual operator, but let's not go into this mathematics. For all practical purposes, we can treat the bra, for all practical purposes, we can regard the bra as a vector in the bracket notation. Not worry about these tiny differences that, and let the theoretical physicist and the mathematician worry about that. So for all practical purposes, quantum mechanics is defined in terms of a slightly different vector product, which doesn't lead, inner product, that doesn't lead to a real number, but generally leads to a complex number. And when you reverse the order of the bra and the cat, you get the complex conjugates of the complex number. And it still is by a linear object. But of course, in the complex field, meaning that I'm, consider linear combination of with complex coefficients. For example, I have that, alpha psi plus beta, maybe call it chi, well, that's, linearity. Chi alpha psi plus beta phi equal alpha chi psi plus beta chi phi, and so on and so forth. The linearity on the other side, of course, involves the complex conjugation. So Hilbert space really do look like vector space with two fundamental differences, infinite dimension, and they multiply by coefficients that can be complex, and therefore when you define an inner product, you have a more complicancy coming from the fact that inner product is no longer a real number, but is a complex number. Of course, let me just make a note here. Note, psi is always real because psi is equal to psi complex conjugate because of this property here, right? Because I reverse now the order, I put this psi on the other side and this psi on this side, and I get psi complex conjugate. And of course, the only numbers which are equal to their own complex conjugates are reals. So yes, the inner product are in general complex numbers, but when you take the inner product of a vector by itself, it is in fact a real number. Now, I want to refresh this page now and talk about projections inside my vector space. And let me add in this page, just to make sure, real vector space. And let me, actually, let's do the following. Let's talk about projections and representation. And we do so by first considering the real vector space. And then looking what happened when we discuss Hilbert spaces. So what is projection? I have a general vector V, which I cannot represent mathematically, but cannot represent numerically. I can only define as an abstract mathematical object that lives in my vector space. So V is defined to live in my vector space V. But then I can define a basis, which I will call, in this case, E1, E2, but in general there are n elements depending on the dimension of the vector space. For instance, E1, E2, and E3 for vector spaces that are relevant for classical mechanics in 3 dimensions. So we define 3 basis vector, and normally they are chosen to be orthogonal. So we define them in such a way that EI dot EJ is 0 for all I and j, and EI dot EI is equal to 1 for all I. These are called orthonormal set of bases. Why we like orthonormality? Because, you know, we don't want redundant information. If you have an orthonormal set of vectors, all you need is, of course, as many vectors as the dimensionality of the space is concerned to write any vector as a linear combination of these vectors. So once you do that, any vector v can be written in the following form: v1 e1 plus v2 e2 plus v3 e3, where v1 is nothing but v dot e1, v2 is nothing but v dot e2, and v3 is nothing but v dot e3. So this representation in an orthonormal basis is unique, meaning that once you choose the basis, there's only one way. If the basis is orthonormal and has as many elements as the original vector space, because you can get, just if your space is three-dimensional, you cannot get four orthonormal vectors. One will be linear combination of the other, right? So as long as you have an orthonormal complete set, every vector can be represented as a unique linear combination of the chosen orthonormal vectors. And it is important to say that, you know, the basis is complete if any vector can be represented, and is also unique, which means that for each vector, you can represent its unique, you can get a unique representation in terms only of the coordinates, which is an element of a specific vector space called F3. So after you've done the projection, after you've chosen your basis, you can forget about drawing arrows and being abstract. You have now a way to represent uniquely, given a basis, every element of the vector space in terms of a set of numbers. And you call these numbers coordinates. And once you've done this, many of the mathematical operations become trivial. For instance, one central property is that if you have inner product, well, this can be written, well, I guess it's quite easy for you to prove it. I will go through the proof. Say this is going to be V1. Oh, I prove it, but I'll be a little bit formal there. Okay, so I use a linear, I represent V as a sum for I going from 1 to 3 of VI EI, and I represent W as a sum from J going from 1 to 3 of WJ EJ. Now I use the bilinearity of the vector space, which will be sum over I, sum over J, VI EI dot V WJ EJ. Right? I've just multiplied these two. Now, let me erase one step above here to complete the proof. I notice that this is an orthonormal basis. And if it's an orthonormal basis, the inner product of two elements is 0 unless the two elements are the same elements, right? So unless I is equal to J. So EI dot EJ is equal to 0 if I is not equal to Z, and 1 if I is equal to J. And this is called the Kronecker Delta. It's represented by a delta with suffixes I and J. And this is a number that, you know, does exactly this. It's 0 if I is equal to J, and 1 is sorry, 0 if I is not equal to J, and 1 is I is equal to J. Kronecker Delta. Okay, having done this, then clearly this sum, instead of ij, I can write it as wi with wj and delta ij, which is ei dot ej, which means that this sum is, it's not equal. Of the two sums are redundant because the j's are non-zero only when they're equal to I. So I can forget about all the j's except when j is equal to I. So I'm going to replace with this I. So this is a fundamental result, and I'm going to copy this all the way here. You can unwind this lecture online so you can go back. And this is basically saying that it's completely straightforward to calculate inner product after you've done the projector. Because what you need to do is basically to take components by components and multiply them and then sum up everything. Now, what about projections in Hilbert space? Well, you can still define projections in Hilbert space. And the first thing you need to do is to define a basis of the Hilbert space. An orthonormal basis of the Hilbert space is one such that any quantum state can be represented by an infinite sum that means with k a basis, any basis. Let me call it, just to be, ek, to keep the notation as close to the classical counterpart as possible. We can write it this way: coefficient stack. And of course, you want that ek el is 0 if k is not equal to L, and 1 if k is equal to L. Now, this is in the case where we have a discrete, numberable infinite set of elements. But in principle, we can use vector space, Hilbert space bases, which are represented by still infinite but continuous elements. For instance, the position eigenstates. So a position eigenstates, these are called position states. And of course, there is one vector state for every point in space. Now, unlike integer points in space can be arbitrarily closed. So how do you define the inner product between position states, where this is going to be 1, 0 if x is not equal to y. And it should be something like 1 if x is equal to y, but it's not 1 because what you really want is the integral. So in other words, what I'm trying to say is that when I have everything discrete, my steps are like from 1 to 2, 2 to 3, and then of course you get a function that is 1 only when the two indices are 0, are the same, and 0 otherwise. But when you go to the continuum, these 2 points can get closer and closer and closer. X and Y can be closer and closer and closer. And from reasons that will become very clear in a minute, you want, that the area underneath to be, so if you only allow this function to be non-zero when the 2 points are exactly the same, you get a function that basically looks like this. It's zero everywhere except in a point. And if you try to treat this as a function, for instance, the integral of this function is always zero. This is the point where x is equal to y. And this is mathematically problemsome. The way you do it, you consider this as a function when x becomes you smear this point and you make it such that for whenever x is sufficiently close to y, then it's basically an infinitely smeared Gaussian or whatever you call. So the way you represent this idea that you get zero unless x is really, 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 really close to y is represented by coded continuous delta, not the Kronecker delta, also called the Dirac delta. Now, the notion of the Dirac delta is a bit troublesome at this level. What you should think, I will spend some time to define it a little bit better later on in the course. For the time being, a Dirac delta is something that is zero everywhere unless x and y are really, really close. So it's a function that is infinitely peaked around x minus 1. But the area of this function remains 1. We'll get more about that in a moment, in a couple of lectures. But this is the concept of orthonormality for continuous function. Now, if you want to represent a state on a continuum state, of course, you need a continuous sum, which is called an integral. And therefore, this quantity is a function of x. And how are the coefficients defined? Well, they are the projection in a product of your quantum state on your basis, just as much as the coefficient di when ei dot b. And these projections are complex, and they're called the wave functions. So remember, we define quantum mechanics in terms of functions. Now I can change my notation from alpha to psi, because this is a quantum state, and it's an abstract mathematical object. It lives in the abstract. And this is the complex function of x. And this is my basis. So when we now look at the inner space between vector, between quantum space, and we use bilinearity, we discover a relationship that is similar to the relationship we use to define the vector's product. Remember, we want the analog of this. So let's consider psi and chi. Remember, when you act on the left, you have to take complex conjugations. So this is the integral dx psi star of x. I use another index, dy, chi of y of y. Now, when you deal with this, you get two integrals, two functions, and x dot y. But now remember, x dot y is this famous delta function. And this famous delta function tells me that this function is always 0 unless x is really equal to 1, which basically allow me to remove the integral over y and replace this with x. And this plays the role of this relationship here. It's the integral of the terms on the left complex conjugate, the wave function, and the terms of the right function. So, once again, it's interesting to see what happens when I take the inner product of a function with itself, psi, psi, and this is going to be the integral of a little space of psi star x psi of x, and this is nothing but the modulo square of x, and that's the normalization. So in particular, we want to set it to 1 if we can. And that's, anyway, it's a real number. So in this lecture, we established an interesting, we established the ground for defining quantum mechanical rules by defining the concept of Hilbert space. And let me remind once again that the Hilbert space is nothing but a vector spaces with different properties. As you know, when the orders of the products are not irrelevant. The first term, when you pull out the coefficients for the linearity, you get complex conjugation. The right term, it doesn't get complex conjugation. So in other words, let me remind what bilinearity means for vector spaces once again. I'm repeating here, but if I say alpha chi1, sorry, alpha chi1 plus beta chi2 psi, this is alpha star chi1 psi plus beta star chi2 psi, where star is complex conjugate. How do I know? Because if I want, because I define to you that this quantity must be the complex conjugate of this quantity, now if I do this and I use the normal linearity, then I get alpha psi chi1 complex conjugate plus beta star chi2, but now I use the fact that this is chi1 psi and this chi2 psi, which gives me precisely this. You see, so this is the main difference between Hilbert space in a product and normal vector places, and the somewhat trivial difference of having infinite amount of bases. When it comes to the notion of orthonormality, in the case of vector spaces, we have introduced the idea of orthonormalities through this operator, of this relationship. This is the Kronecker Delta. And being a little bit sloppy at the moment, we'll deal with that next lecture. We have introduced a similar concept through the so-called delta function, which is a continuous generalization of the Kronecker function. And at the moment, we have intuitively considered this as a function that becomes non-zero only when x and y are very close to each other, so the argument is 0. So the function of delta of z, so to say, is a function infinitely peaked around 0. But not just as a point, otherwise I'm losing the probability of integrating this function, because the integral of a function that is 0 everywhere except the point is 0. But basically, it's a function that is as peaked as I want, but retains a unit area. It's somewhat difficult to imagine. So basically what you do, you consider, for instance, a Gaussian with an infinite smear there with some width, and then you take the limit for this width that goes to 0, retaining the norm of the Gaussian. Then the Gaussian will become higher and higher as you take sigma smaller and smaller, and when sigma is really 0, close to 0, it will be infinitely spread. So these are the two main differences, and with this we constructed the concept of vector and projector. What is left to be doing is generalizing the concept of metrics and operators. I will deal with that in the next lecture.